Oftentimes when we're dealing with electric and magnetic fields, it's very important to know the distance between certain points or the position of various points so that we can determine some value. So because of that, we're going to now look at position and distance vectors. So in order to make this a little more easy to understand, let's consider 2 points in a Cartesian coordinate system. So we're going to consider 2 points in a Cartesian coordinates, and so our 2 points are going to be P and Q. So for our point P, we're going to say it's at some point x sub P, y sub P, z sub P, and then for our point Q, we're going to say it's at x sub Q, y sub Q, z sub Q. And so notice again, I'm using just parentheses as opposed to angle brackets because now we're talking about a point in space as opposed to a vector. So let's first define our position vector. So our position vector is essentially what's going to allow us to define where our point P is in space or our point Q is in space. And so you'll also sometimes hear this called a radius vector. And so what this is basically just the directed distance from the origin to our point of interest. So of course, if we have a vector, we're talking about a direction, so that's why we have directed distance from the origin. Let me write that a little clearer. So from the origin to the point of interest. Okay, so let's say we're considering point P. So if we want to find the position vector for point P, our notation would be lowercase r sub p, and of course this is a vector, so we're going to put an arrow above the top of it. You'll also see this sometimes written as OP, and the reason for this is because we're going from the origin to point P, and this is going to be equal to, well, our point P is up here. So we see we have xp in our x direction, so xp times u of x, our unit vector in the x direction, plus y of p in our y direction, so y of p times u of y, plus z of p times u of z. So that would be our position vector for point P. So now let's say we're also interested in the distance between points P and Q. So if that's the case, we want to use something called a distance vector. And so basically what we're going to see is that our position vector is really sort of a special case of our distance vector where one of our points is our origin. So our distance vector is simply just the displacement from one point to another. So a displacement from one point to another. And our notation is going to be somewhat similar to that we see above for our position vector. So we're going to have a lowercase r with an arrow over it. And just to be really general here, we're going to have 2 subscripts on our r, and it's going to be our start point and our end point. And we'll see an example of that with our P and Q in a little bit. And what that's going to be equal to in terms of the combination of the 2 vectors is we're going to have our r at our end point minus our r where we're starting at. And so basically what this is telling us is that if we're looking at the distance from P to Q, that's going to be opposite from the distance of Q to P. So the direction is just going to be flipped around because we're going to flip this operation. Okay, and again, as I mentioned, our position vector is just sort of a special case of that distance vector. So let's say we want the distance vector from P to Q. So our distance vector from P to Q, and notice these are just points, they don't have any arrows above them. Well, we can find that as, so this is going to be our r sub P, Q, because we're starting at P and we're going to Q, so that's our start end. And of course we need an arrow over our r because it's a vector, and we know this is equal to our end vector, which is Q, so r sub Q minus r of our start point, which is the end of our vector P. And if we actually go through and do that, what we get is that this is going to be equal to xq minus xp in our x direction plus yq minus yp in our y direction plus zq minus zp in our z direction. And so of course we can look at this graphically as well, so this distance vector from P to Q. So let's say we have some point here, which is our origin. So I'm going to mark that with an O, so that's our origin. And let's say, again, just kind of arbitrarily putting these points, let's say this is our point P, and let's say this is our point Q. So first of all, we can draw in our position vectors. So let's do our position vectors in blue. So we would have a position vector for P, so this would be R sub P, and a position vector for Q. So this would be R sub Q. And so in blue then we have our position vectors. So now if we wanted to do the distance vector from P to Q, so let's do that in red. So from P to Q, so again, that's indicating we have a certain start and a certain end. We're going to be starting at P and going to our vector Q. So we have something like this. So this is R sub P Q, and that's going to be our distance vector. And again, these are going to be very important ideas as we start looking at distances and positions of various charge particles, charge structures, charge densities, and talking about what type of fields and forces arise from them.